My name is Janine Keith. I co-lead the SAM team here at NREL, and we're excited to talk to you today about how to model these projects. This is part of the larger SAM webinar series for 2023. This is the fourth one so far, and there's one more. Next up is modeling behind the meter batteries in SAM. The webinars are free. You just register in advance at the website shown on the screen. And we do also record these webinars, so they will be available on the videos page on the SAM website, sam.nrel.gov, and posted on YouTube for anyone who wants to watch but isn't able to join live. Just a quick housekeeping thing before we get started. You can ask us questions. We plan to leave a bunch of time for Q&A at the end of today's presentation. My colleagues are also on the GoToMeeting, and so they will be monitoring the questions. You can type your question into the box shown in the screenshot on the left here, or the questions icon if you're joining via the Instant Join viewer. And my colleagues will either type an answer to your question, or they will hold it for the end of the presentation and then read questions live, and we can follow up as needed. The agenda for today is relatively short. My plan is to do a sort of quick and high-level overview of utility scale PV system modeling in SAM and leave plenty of time for Q&A. So we're going to do some quick discussion on slides of utility scale PV and then switch right over to a live demo in the SAM tool. I'll then bring it back to mention a couple other resources that are available past just this webinar for digging in a little more detail, and we'll flip over to Q&A. Many of you probably are already familiar with SAM, the System Advisor Model. It's free software that enables detailed performance and financial analysis for renewable energy systems, available as the desktop application, which is what I'm going to be demoing today. And also a software development kit that has a Python package, and the code building all of it is open source. So there's various open source repositories that you can find the algorithms in. And I wanted to talk quickly about what is SAM's definition of utility scale PV, because the interesting thing that I think is important to note is that SAM doesn't actually enforce any specific definitions of scale from the technology side for PV. It is up to the user to choose the combination of technology and financial model options that make the most sense for their system. The important distinction is actually with the financial model. The financial model differentiates between whether a system sells the power that it generates, in which case a user would want to pick one of our front of meter financial models, or whether it reduces the owner's electricity bill, in which case a user would want to pick one of the behind the meter financial models. There are more information on both of these financial models as well as videos on the SAM website. I am not going to be talking about the financial models today, but what I will be showing is how you can use the detailed PV model to model a large ground-mounted single-axis tracking system with central inverters. But I did want to note that it does not have to be a specific size. You could model a 4 kilowatt system or a 100 megawatt system in the detailed PV model the same way in any of the scales. It really just matters what the financial model associated with it is as far as defining the scale from the SAM perspective. So as promised, I'm going to go ahead and switch over to a live demo. This is our latest public release of SAM, released in November last year. We are planning an updated release this fall, but a lot of the information I'm going to show here will still be relevant. So I will go ahead and demo here. I'll click Start a New Project. And you'll notice that there are actually a few model options available for photovoltaics. The two most relevant for general PV would be the detailed PV model and PVWatts. PVWatts actually uses the same algorithms under the hood as the detailed PV model, but it makes some assumptions for some of the inputs so that there are far fewer inputs that the user has to pick. Now, this does not mean that it is necessarily a simpler model, and PVWatts can actually be an appropriate choice for many modeling applications, even though it has fewer inputs, particularly folks who might be interested in doing more of a quick siting analysis. You're at the very early stages of planning, don't have technology choices, et cetera. Or folks who are looking more at policy or more concerned with the financial models, PVWatts is a great choice. Today, I am going to be demoing the detailed PV model, which has, as it implies, more details available as far as inputs for the physical layout of the system, the electrical layout of the system, and the actual equipment used in the system. So if I click on the detailed PV model, you'll see that the financial model options show up. There are, as we mentioned, a variety of different financial model options at different scales. There are utility scale financial models for front of meter systems. There are behind the meter financial models. Since I'm focusing on the technology model today, I'm going to go ahead and pick no financial model and then click OK to open up the case in SAM. For anyone brand new to SAM, the navigation is along the left-hand side here in tabs. Inputs are organized into groups of like inputs. And then across the top, you can create different cases. I'm going to show only one case today for a bit of an overview of how to set up a large PV system in SAM. We'll start with the location and resource page. Here we have the solar resource library. SAM uses weather data for a specific location that includes at least 2 components of irradiance, as well as temperature and wind speed. We provide a handful of files when SAM is first installed on your computer, but you can also download weather files for your location in this download box here. So I will go ahead and download a weather file for Denver, Colorado. And I'll note that here you can pick whether you want the default typical meteorological year, you want to choose a specific year, or you want to download all of the available years. And this weather data is coming from the National Solar Radiation Database that NREL produces, the Physical Solar Model version 3 at the moment, PSM v3. There is more information about weather files on the SAM website if you want to check out what types of resources are available. I will note a couple of things that you could check this advanced download box as well, which would open up a different dialog box here that allows you to find all of the available data from the NSRDB for a given location. This is also how you would access any available NSRDB files outside of the US at the moment. We do not have full global coverage, but there are files that are available in some locations outside of what can be accessed just from that normal download box there. And I'll uncheck the download button just to show you this download function for Denver. I am going to pick the default TMY file and download it and add it to the library. While it's doing that, I will mention that we do have SAM on the weather page on the website has links to other possible data sources that you might be interested in. There is a log file that shows what files were downloaded for the given location. I'm not going to open that now, but you can open it to get more detail. And you'll see that it has highlighted the new file, which has been downloaded and added to my library. I can also take a look at the data that's in that weather file just to make sure it's looking as I expect. So right now it's showing me the beam irradiance or the direct normal irradiance for my location. I can zoom in and see that it does look like Denver in May in this case, with some days that are partly cloudy, some days that are quite sunny. So this is looking right to me, but you can investigate a little bit further without having to actually simulate a system. I will mention that on this page is also where some of the advanced irradiance features are that utility scale modelers might be interested in. This is where you can set a sky diffuse model, you can pick which components of irradiance are being used from the weather file, and you can also set the albedo in a couple of different ways. We do have albedo as part of the weather file from the National Solar Radiation Database, so that box is checked to use the albedo from the weather file if it is available. If you don't know what any of these features mean, these are set to reasonable inputs and you can safely ignore these unless you have a reason to change them. Next, I'll go ahead and go over to the module page. So this is where I would specify the actual module that is going to be used in my PV system. By default, we open to the database option. So this is a database of modules that comes from the California Energy Commission that SAM uses to ingest the information on module specifications and parameters to use within our model. There are thousands of modules available in this database, and many of the common ones are available. So I'm going to go ahead and just pick a Trina module. You can see that by typing in the name here, it shows me still the currently selected one, but then all of the other ones that come up as part of my search. I'm going to go ahead and pick this just 220 module here, and you'll see that I can take a look at the IV curve and the specifics of the module parameters that have been imported from the database here. This database is updated once per year, usually with our release with the most updated information from the California Energy Commission, and the same is true for the inverter database that I will show shortly. If you are trying to model a module that is not available in the database, or you have better information for your module, by clicking on this arrow here, I can actually access several other module models. I'm not going to go into them in great detail, but I will point out that the user entered specifications option is the one that would be most commonly used if you have a data sheet for a module, but you can't find that module in the database, or the parameters in the database don't match your data sheet. That would be the option to choose. I'll click it quickly, and you can see that there's just inputs to enter a lot of the common data sheet parameters, and then you can calculate and plot the IV curves that would be indicated by those parameters. I'll switch back to the module database here. And I want to quickly mention that the module page is also where you would specify bifacial modules. So this section right here, it's in a slightly different spot for each module model, but it is available for each module model. I can check that the module is bifacial, and then there are a few additional inputs that I can specify, hopefully available on the data sheet for the module as well. And this is also where the ground clearance height for the system would be specified here, because that is very important for the bifacial model. I'm going to uncheck it because today I'm not going to show a bifacial system. And if I scroll down a little bit, you can see that this is also where the temperature model is specified. So by default, SAM uses a nominal operating cell temperature method. There are some details and links in help, which is located in the upper right-hand corner here, that talk a little bit more about the details of the model. But you can pick mounting standoff. So this, again, the default is set correctly for me, ground or rack mounted system. This changes some of the parameters of the thermal model. And my array height is going to be 1-story building or lower because I'm building a ground mount system. So this is where you would specify some of those thermal model parameters. Next, I will go to the inverter page. Again, by default, we have a library of inverters that are shown here, more information that comes from the CEC and is updated once per year. I'm actually going to go ahead and stick with the default inverter selection here, but once again, much like the module page, you can filter by name. You can also sort any of these column headers. If you're looking, for example, for a specific size inverter, you could sort them here and scroll to the size of interest. And then you can take a look at the efficiency curves and the specifications for this inverter. You can also specify a temperature D rate for your inverter if it's going to be operating in very hot environments. You can specify multiple voltage curves and what temperature the D rate starts to occur at. And once again, much like the module page, there are a few other options of inputting your inverter information. The most common alternative method would again be the data sheet. So this is meant to be able to ingest parameters that are commonly available on an inverter data sheet. So if you have an inverter that's not available in the database, this is a great way to input it. You can also input part load curves or generate the coefficients for the CEC model if you have the appropriate data pieces. Next up, we'll head over to the system design page. This one specifies both the electrical and physical configuration of the system itself. It's sort of a busy page, so I'll spend a few minutes walking through the options here. Up on the top right, there is a sizing summary box. So this is going to tell you the amount of nameplate DC capacity, so the modules that are currently installed, the AC capacity, the inverters that are currently specified, the DC capacity of the inverter, and then some of the other specifications about the total number of modules, number of strings, and the area that that takes up. So this is really summarizing what you've managed to specify. It's a great thing to reference to double check that you've input your parameters the way that you want to. I'm also going to point out that you can estimate this subarray 1 configuration. This can be a helpful shortcut if you don't necessarily have an exact system layout yet. If I check this box, you can see that some of the inputs got grayed out, and instead I just specify a desired array size and a desired DC to AC ratio, and SAM will do some calculations to get as close as it can to that specified DC capacity and the specified DC to AC ratio. You can see in this case, the calculated one does match the specified one exactly. So that can be a good starting point for a system, but you can also just specify what you would like. So for example, I'm going to change my system to a nice even number of inverters here. We'll make it 100 inverters. And you'll notice that that changed my DC to AC ratio a little bit. And this is also where I could modify the number of modules in string down here and the strings in parallel. You can set up to 4 subarrays in one case for a PV system. Subarrays in SAM would indicate that there are differences between either the electrical configuration or the physical configuration between different chunks of the system. So many PV modeling tools specify things in blocks, and you have to specify multiple blocks even if they are the same. In SAM, it's a slightly different paradigm, where you're only specifying multiple subarrays if there is some type of difference between the subarrays. If I go ahead and make the number of modules per string 10, which is pretty low for this combination of modules and inverters, I can scroll down here and see that there are some sizing messages that show me that the nominal operating voltage of the string that I've specified is lower than the low end of the maximum power point tracking voltage range of my inverter. And it suggests a fix for that. Now, I will note that all of the sizing messages that appear in this window are based on nominal VOC. We do have a system sizing macro, which I will show quickly. Macros are down in this corner. And you can select the system sizing macro. That would allow you to do a slightly more robust sizing calculation considering your specific module and inverter. I will note that we are actually going to update this macro for our fall release, we hope, to have it take a look at adjusted VOC in a slightly more robust fashion that better matches what industry is actually required to do by various code regulations. So I'll go back to my system design page and scroll back up. I know that 10 is not a good number of modules for a string, so I'm going to go ahead and change it back to 22 here. And then this is also where I would specify my physical configuration of the system. So in this case, I'd actually like to specify a one-axis tracking system. That's pretty common for large systems like the one that I'm trying to design here. And you'll note that this tilt input did not automatically change to 0. Unfortunately, we don't have that type of capability integrated at the moment in the user interface. So I will have to manually change it to a 0-degree tilt. If you do try to run a simulation with a tilted one-axis tracker, you will get a simulation warning. So at least we try to help people a little bit in that way. This is also where I would enable backtracking. I'll go ahead and do that for this system. You can see that I can set the tracker rotation limit. I can specify my ground coverage ratio, or how close together my rows are. And the azimuth, I'm going to go ahead and leave at 180, which in SAM's convention means due south. And since I am modeling a system in the northern hemisphere, this is what I want it to be, the way that I want it to be pointing. With the backtracking, I am able to set 2 degrees of terrain slope. They are simple terrain slope, continuous and not varying terrain as far as what's available in SAM right now. Next, I will go ahead and show the shading and layout page. We have a couple of different options to input things on this page, so I'll quickly walk through them. We do have a 3D shade calculator. This is meant to help specify the shade from nearby objects, such as trees and buildings. So this is really more common for use in smaller systems where you're not trying to draw several megawatts of panels. So I am not going to use that for this system. Instead, I'm going to use the box below it, which is the self-shading algorithm. So this is meant to take care of shading of modules in the array that occurs from a neighboring row in the array. You'll see that here we have 3 options for self-shading. You can specify that there is no self-shading. You can pick a nonlinear model. So that means that if there is, say, 20% of the module shaded, SAM will do some calculations, because in many modules that will result in more than 20% of the power being lost. But there is also a model here that represents linear shading. So if 20% of the module is shaded, 20% of the power is lost. That can be a better representation for thin film systems, or it can be a slightly less conservative estimate of your self-shading. So I'll go ahead and select the nonlinear shading, because I do have a silicon module that I would expect to respond nonlinearly to some self-shading. And then you can see that more inputs were enabled by making that selection. There are a few diagrams down here that try to help you understand what the inputs are referencing. The module orientation portrait, meaning that it is longer going up than it is wide, is a pretty common configuration for utility scale systems. The 2 modules along the side of the row here represent how many high up on a rack you have. And then the number of modules along the bottom of the row represent just what it describes, how many modules go along the bottom of a row. I'm going to change this input to 22, which matches the number of modules in a string for the system that I'm specifying here. So basically each row would contain 2 strings, one on the bottom and one on the top, with the way that I have it set up here. This page also imports some information about the module size from the module page, but you can change the module aspect ratio to better match yours for shading purposes. I'll mention also that we do have a model that allows you to estimate the snow losses on a system. That does require snow depth data in your weather file. I'm not going to do that right now, even though Denver does experience snow. But it uses these same specifications for the self-shading model to set up that snow model in SAM. The second to last page here, losses, goes through the simple D rates to the system. So things that we are not modeling with specific models, but we are rather just using simple D rate factors to do. I have soiling up here in the top, and I'll note that you can modify the soiling monthly. So maybe I'll say that it rains a lot in Denver in May and June, and that's going to lower my soiling percentage in those months a little bit. You can also apply a single value to all months in this dialog box here. I'll go ahead and click OK. And it does calculate the average annual loss, although that is not how it is applied. It is applied month by month in the actual module. Then there are a variety of other losses here. We provide a couple of buttons to set the defaults appropriately for the inverter type that you have or DC optimizers. I am using a central inverter, and those are the default values, so it's not going to change anything if I click that button. And I'm going to leave all of the other losses at their default values, but note that we have losses available on the AC side, in addition to the DC losses I showed up here. We have a simple transformer loss model, a transmission loss input, and then a few losses that are actually able to be time varied. So you could apply just a simple constant loss on the DC or AC side, a time series of losses, or custom periods, which you might use to enable known maintenance on the system that's going to take the entire system offline, or things like that. The last page here is the grid limits page. This is where you would set if there's some kind of interconnection limit, and the power would be curtailed if it's calculated above that limit. This is something that utility scale PV systems might encounter sometimes, so wanted to be sure to set that. And you can also set a time series for grid curtailment if that's something of interest in your model. If I go ahead and click the simulate button, I can take a look at the types of results that I get from my system. So this, because I did pick the no financial model option, is a fairly short metrics box here of some of the high-level metrics that are available. It shows me the annual energy, the capacity factor is 22%, kilowatt hours per kilowatt, and performance ratio. It shows me a graph of what the AC energy looks like and a heat map of the annual AC energy in an hour by day graph here. You can also get to a lot more outputs in the data tables box here. By default, the system power generated is shown. It is negative at night, representing inverter tear losses. But I can look through a variety of different inputs as of interest in this screen here. I can also take a look at a loss diagram on this page, which can be a helpful pointer of, did I do anything horrendously wrong in setting up my system? You can see that the soiling does set up to be roughly that annual average that we specified on the losses page. Module deviation from STC represents losses from the fact that your actual weather is not standard test conditions, so 1,000 watts per meter squared and 25 C all the time. You can see that there might be a little bit of maximum power point clipping, and then several of the losses that were actually specified. And if I scroll down, I can get all the way down to my net AC electricity that's going to the grid. The other output page that I want to highlight is this time series page. So this lets you view, for example, this one is highlighting the system power generated by time, so looking throughout the whole year, and you can highlight a section of this to scroll in a little bit, take a look at a particular day if you're interested, and scroll through the results to make sure that they look sort of how you're expecting. And once again, you can select a variety of different results to view on this time series viewer here. I will mention another feature that can be very useful for utility scale analysis is parametrics. We do have other videos that I will reference for how to use that feature, but I want to make sure folks know it's there. That allows you to vary inputs and view their effect on a certain output in a pretty quick way without having to manually vary the input or know how to script that. And with that, I will go ahead and flip back over to my PowerPoint just to talk about a couple of other available help resources and things that might be helpful when looking at utility scale PV systems. And after that, we can go ahead and flip to Q&A. The one that I really want to highlight is we do have an extensive help system. Kudos to our technical help guru, Paul Gilman, who writes a lot of that content. So from the SAM software, you can click help or press F1. It is context sensitive, so it will tell you about the page you are currently looking at. And there is a PDF version available on the SAM website as well that you can browse or scan or search for more information. We also have a forum on the SAM website, sam.nrel.gov/forum. You can find information that has been questions that have been answered on the forum. You can have a discussion. And you can also register on the website. It's a free, easy, quick registration to post questions or respond to other people's questions and have a discussion about what you're trying to do. We do prefer the forum method for the majority of help inquiries because it is searchable. The answers are available for other people to look at or to comment on if someone else is having the same issue as you. But we do have an email, sam.support@nrel.gov address as well that is monitored and can be a useful way to send files that might have information that can't be posted publicly, etc. Or if you're interested in working with us, that's also a great place to get in contact with us. Some related resources specific to the PV that I have mentioned here are all on the SAM website. So you'll notice that the address specifies sort of a topic area, and then there are some subpages within that. So if I go ahead and click this link just to show you the SAM website in case you haven't checked it out yet. It is going slow for some reason, but you can see this link brought me to the section here. Photovoltaic is listed at the top, and there's PV videos, publications, information about the cost and component data, validation of the model, and a reliability performance model. So all of those links are available on the website. We have a video on bifacials specifically on that reliability performance model. We have a detailed video about sizing PV systems, and although some of the screenshots are a little bit different in that video, the information is still relevant. And then, as I mentioned, we have information about validation of the PV model. We have some information about financial models, which would be useful if you're trying to couple a financial model with your PV model here. And then because batteries are really becoming very important to a lot of PV systems, I also wanted to point out the page about battery modeling. So if you're interested in adding a battery to your PV system, we do have some information for you there. And as I mentioned, the SAM website has a bunch more resources. So if there's something you're looking for, definitely check it out and see if we might have what you're looking for. With that, I will go ahead and wrap up this part of the presentation. Thank you all for your attention. And I look forward to answering any questions that might come up.
Thank you, Janine. We do have a few questions that came through the questions widget there. The first one maybe you could take a minute to address is about multiple subarrays. And just a question about whether you can specify different tilt angles for different subarrays. So might be worth just showing how that works.
Yeah, for sure. Let me go back to my system here for the system design page. I can specify multiple subarrays, which I'll do a quick demo of here by checking this enable box, and then you see all of the inputs show up here. So let's say I want to specify maybe those last 640 strings being on a different subarray. I could change this down to 20,000 strings. You can still see the number of strings total is available up here, and the total capacity listed here, which is not quite right yet because I didn't specify a number of modules in these strings. So there is my my capacity right there. And then I could do 2 single axis tracking systems. That would be a little silly, but in this example, let's say I want to have 2 different sections of an array that are at different tilts. So maybe most of the array is at 20 degrees, but for some reason this section here had to be installed at 15. I can go ahead and do that. Maybe it also has a slightly different ground coverage ratio. And maybe it's slightly west rather than due south. I can change all of those things. Go ahead and click simulate. And then let me show in the time series here, I can actually search. I hope it's not working on my machine for some reason, maybe because my buttons are blocked by the GoToMeeting thing. But I can go ahead and take a look at some of the information for the different subarrays here in the time series. So maybe just the angle of incidence difference between Oh, there it goes. My computer's being slow to load here. Let's take a look at the angle of incidence between subarray 1 and subarray 2. You can take a look at how those are different here. So that's just a quick example of how this is all set up for multiple subarrays within SAM. Hopefully that helps answer the question.
Yeah, and I think another point is if you wanted to model each subarray operating at different voltages, then you could enable the multiple MPPT inputs on the inverter page.
I don't think that's available when you have multiple inverters.
Right. So if you're doing a residential scale rooftop system, then
yes,
that's possible. Otherwise, for a large scale system with multiple inverters, the assumption or SAM just averages the voltage of each subarray and treats that as the inverter input voltage.
Yes. Thank you, Paul.
See, there's another question, a few questions here. The next one is about the layout on the shading and layout, kind of the modules alongside of row and bottom of row, how they compare to the string, the electrical layout on the system design page.
Okay. Yeah, I can talk a little bit about that. In an ideal world, you would have, each complete string from an electrical perspective would be located on a single row, right? They would be together. One half would be on the top, one would be on the bottom. In the real world, that's not what gets installed. So there are some assumptions that this model will make. So for example, say that my racking design requires no more than 40 modules on a single rack. I picked a bad number because Sam isn't going to complain about that. Let me pick 17 instead. There. Just to get this error message here, which is something that you could see when you're trying to set these inputs. It tells me that the number of rows in subarray 1 is not an integer, and to adjust the number of modules to correct the problem. Now, this is more of an indicator message, so it's telling me to double check my input because it's calculating, 12,941.17 rows, which is not actually what's going to be installed. That said, it is not, you can still simulate the system this way, and you might legitimately want to if your electrical stringing isn't going to perfectly match your physical row layout of the system, which is a legitimate thing that happens in real utility scale systems or even residential scale systems. So what it will do in this case is it will use these inputs to calculate the shading, and it will apply that shading to the full system, which is a reasonable assumption for most large systems. Let me go ahead and disable this second subarray here just for simplicity's sake. When I go ahead and take a look at this, I can simulate it. You'll see that I get that same warning again, but I can click OK. And it will calculate if I go back to the data tables and look for shading. I can look at my self-shading beam irradiance, for example. I guess I have my ground coverage ratio pretty far apart, so let me make that a little bit higher, which will put my rows closer together so that we can actually see some self-shading. I have to move my, there we go. Boy, apparently I still didn't put them close enough together. But it would be calculating, here we go, I'm looking at the wrong factor. In this case, the model calculates a nonlinear shading factor because I did pick that nonlinear shading algorithm, and that factor I had forgotten is applied on the DC side of the system because that is how the model was formulated. Obviously, the actual shading phenomenon happens by derating the irradiance in the world, but the model was based on some empirical correlations with DC power, so that is where that factor gets applied. And you can see that it's just calculating a factor that's getting applied to the entire system, even though the number of physical rows didn't match up with the number of electrical strings.
Great. Thank you for that. The next question is about using SAM to model an existing operating solar plant. And the question is, what are the key parameters to pay attention to? So if you've got measured weather data.
Yeah, that is a great question. We've actually done this type of exercise when we were validating SAM's photovoltaic models. The most important thing that I hope I noted, but I don't recall, is that on the location and resource page, SAM can use any weather file as long as it is formatted a certain way, and that format is described in help. So you can actually point SAM using these buttons to particular files on your computer that you may have made using the measured weather data. So that would be the most important thing, would be to use either weather data that you've measured for the system or to pick the concurrent year. So choose an actual year of data so that you are comparing apples to apples on the weather file side. And then you would want to pick.
Janine, sorry, do you want to show the POA input?
Yes, that is a great idea. So one of those advanced options that I mentioned, we are able to directly ingest measured plane of irradiance data, either from a reference cell or a pyranometer. So if that is available in your weather file, it needs to be labeled a certain way. I believe the title is just POA, but that's described in help. And then you would select that option. Or this is a great example of an application where maybe you have measured GHI and DHI, and so you would want to pick that combination of inputs here instead of the default DNI and DHI. But you can also ingest POA data directly, which is frequently more commonly available. On the module page, you obviously want to pick the exact module that you have. And if there are any differences between what's in the database and your module, you would want to switch to the user-entered specifications to get that to match up. Or you could use, we have a method to ingest IEC 61853 test data. So perhaps you have that for the module in your system. You could use that option as well. Again, same thing with the inverter. Pick the actual inverter that you have. And then the system design, you would want to specify all of these inputs to make sure that they match both the electrical and physical layout of your system. Shading would be dependent on, for an actual installed system, you probably have some sense of whether it experiences a lot of self-shading or not. And if there is external shading, you can actually import shading information in a variety of different ways that we talk about in another webinar, but that could be useful for an existing plant where you maybe have some measurements if it is near some type of obstruction. And then losses, it's really hard to compare against measured system data because you, in most cases, still don't know exactly what these losses are. And so you have to make some assumptions. You could use the default assumptions here. Perhaps you've actually measured the soiling and you would want to edit that to match what you've measured. You might want to increase one of these DC losses, maybe the nameplate one, if your system is a little bit older, to account for some of the degradation that has occurred. I'll note that there is a degradation input when you couple a PV model to a financial model. It's not available for the no financial model option because that just models a single year of data. But the financial models are modeling a number of years that you set. And so they do apply degradation in subsequent years. But you might want to start your system with some level of degradation if it's been installed for a while. And then the other note on losses is that because they are difficult to know, you may end up seeing a bias shift in what model, any model, SAM or any other model, is predicting for power generation versus what you're seeing. You can, take a look at the outputs and compare them to measured data to identify that bias shift, and then set the losses accordingly to move your outputs up. Or you could use the losses to make the total annual energy match exactly, and then take a look at how the model is varying on a time-step by time-step basis with your model. And I will note that you can model down to 1 minute data in SAM, so it doesn't have to be hourly data. So you could compare if you're measuring, on a more frequent time resolution, you could compare to that measurement with modeled data output from SAM as well. So the losses can be a little tricky when you're comparing to measured data, and you have to make a judgment call for what exactly you're trying to accomplish with that comparison. But that would be the overview of what I would do trying to compare to measured data.
Great, thanks. The next question is about clipping losses. Could you briefly describe MPP clipping losses?
For sure. So on my system design page, you can see that it summarizes the maximum power point tracking window of the inverter. So what this means is that for an installed system, you might install more DC capacity, so modules, than your inverter's AC capacity are capable of handling. And the ratio between the amount of, the rated power of the DC side of the system and the rated power of the AC side of the system is what we call that DC to AC ratio. It is pretty common to see DC to AC ratios over 1, averaging more like 1.2 to 1.3 for utility scale systems, partially because there are some losses that you need to overcome on the DC side to get the rated output power from your AC inverter, and partially because it can be cheaper to install more DC panels rather than a bigger AC inverter, and then you just end up with a slightly flatter generation curve. So let me go ahead and demonstrate that real quick. I'm going to start a fresh case so that the various changes I've made thus far don't impact it. But if I go to my system design and just decrease the number of inverters pretty substantially so that I get a pretty high DC to AC ratio for explanation purposes. If I go to the time series of my generation and zoom in on a couple days, you can see that as the power gets to the peak of the day, it's getting clipped by the inverter. So what that means is that the inverter, the modules are producing more power than the inverter is capable of inverting into AC power. So it only produces its rated output. Now, we do have some, with that maximum power point tracking window, if your number of modules in a string results in more voltage than this window can accept to track the maximum power point, SAM will actually model the inverter controlling the modules to operate off of their maximum power point in order to reduce the voltage coming into the inverter. So you can see sort of the full effect of those losses. You can see the clipping in the middle of the day on the time series page, but you can get a quantification of the losses in this loss diagram. I've got the MPPT clipping here is one of the categories. So that's if the voltage itself is going over. And then this one is the power clipping. So that's when just the power being predicted from the system is still more than the inverter can output. So sort of two different categories of clipping shown here. And you see that this is actually the primary one that I've set up in this simulation here, 8% clipping loss, which might be something that a real system has. And a little plug for the battery model, we do have the ability to connect DC connected batteries that can capture clipping losses if that is something that an operating plant is considering, or a plant under design consideration is considering.
Great. So yeah, the questions are coming in fast and furious. I think we'll maybe have you address one of them, and then as a team try to address the rest in the question window there. So let's see, maybe a good one for you to cover would be, there's a question about the difference between the detailed PV model and PVWatts. That might be helpful to do with a demo rather than
For
trying to
sure.
do by typing.
For sure. I'll go ahead and add a PVWatts case. Like Paul said, that's probably the fastest way to show the difference. So the location and resource page and the grid limits page are the same as what was in the detailed model, but you can see that the system design page is much simpler. So all I specify here is a nameplate capacity, a module category. So standard represents, sort of your regular efficiency modules. Premium would be high efficiency, and thin film have their own lower efficiency and different temperature characteristics. You can specify your DC to AC ratio, which will cause it to calculate the inverter size. You specify the inverter efficiency, and then what type of mounting structure. So I can still do one-axis tracking, for example. My tilt azimuth GCR and some losses. And then we do have a couple of inputs that we classify as advanced, which would be setting up bifacial with the accompanying albedo, monthly soiling losses, and some shading, and a system availability loss. So that is the extent of what's available in PVWatts. As I mentioned, it does under the hood actually use the same module and inverter and thermal models as the detailed model. But we make a lot of assumptions to assume away some of those inputs and levers that are available for the detailed model. And the biggest difference that you'll notice is that there's no information about the electrical layout of the system. And that is, again, because we make some assumptions for a pretty regularly laid out, reasonable electrical design on the system that isn't going to do a bunch of clipping or anything like that, other than power clipping if you were to specify a pretty high DC to AC ratio. So as I mentioned, this model can still be pretty useful for a lot of, early stage design, or I'm really more interested in comparing sites, or I want to know how I need some PV profiles to examine a utility rate design or a policy question, that kind of thing. There are a lot of reasons to use the PVWatts model, and in fact, it is pretty heavily used internally at NREL as well for a lot of those larger scale studies. But that's a sort of a high-level overview of the differences between them.
Great. Let's see. If there's another. There's one question, I guess, about weather data. Just maybe a little clarification on where to find weather data outside the US.
Gotcha. I'm going to go ahead and visit this handy dandy link to the SAM website, where Paul has put together a great page here. This shows the NSRDB data viewer, showing what is available for download from the NREL NSRDB website. And you can download files in the SAM CSV format directly from that website. There are some files that are not directly available from within the user interface, and please correct me if I'm wrong on this, Paul. This part's a little fuzzy for me. But I believe that, for example, some of go ahead.
All of the data from the NSRDB is available through the SAM interface using that advanced download option.
Right.
Yep.
Okay, so the difference then being that you might not be able to just type a location in here, right, somewhere internationally, but if you use the advanced download box, you could access some of those international
Right.
locations.
Right. So when you type a location here, you get a list of all of the available files for that location. So it's a more robust way to interact with the NSRDB data set. Whereas the option, the basic option on the input page itself only provides access to a subset of the NSRDB data.
Yes. And then there's also a few descriptions of some other solar resource data sets that we know about that are freely available. There are some paid sources that we know of that we've listed out here as well. But as we mentioned earlier, any data can be formatted to be used in SAM, either manually, or we do have a macro that can help convert some common file formats to the SAM CSV weather file format. And there's a list of some of those here.
All right, I think we've tackled all the questions, and yeah, so running out of time too. So
Great. Well, thank you to everyone for your attention and for your great questions. And if you have remaining questions, you're always welcome to post on the forum, search the forum, check out some of our other videos, or email us. And we look forward to hearing from you or working with you at some point in the future. Thank you all.